This is Earth Science Lecture number 20 on rock deformation. In this lecture, we're going to look at the various processes which we refer to as stress and strain and what they are and how we could tell the difference between the two. And then we'll examine how rocks can deform in various modes with elastic, brittle, or ductile deformation and what controls which one will develop. And then we'll examine various landforms that can develop as the result of these different forms of deformation, various faults and folds. Now you might wonder how it's possible to deform a rock. Isn't it solid? Actually, if you subject a rock to great enough forces, it can actually bend and break. What sort of force could bend or break a rock? Actually, the forces are those that are related to plate boundary interactions. The strongest forces are found at convergent plate boundaries. And so if you see folded rocks, you can get an idea of what's inside of a mountain range. Currently, the world's largest mountains, we can't see these folded layers because they're way down inside of Earth's crust. But if you could scrape all the layers on top of the mountain away and look at what the mountain looks like at its core, you could get an idea of the intense geological stresses that are present to actually bend the rock and deform it. Now, there's a science called structural geology, and this is by looking at various geological structures, such as landforms called folds. Some folds are shown here in this picture where the rocks are actually twisted and bent around, so the layers completely twist around and fold over. There's also a landform called a fault. A fault is where rocks slip past each other along a planar surface. By looking at the various types of folds and various types of faults that develop, geologists can actually infer what kind of deformation occurred in a region in the past. So certain structures will form under certain types of deformation. Like for example, if you see folded rock layers, that tells you that in the past there was a lot of compressional stress. And we'll see as we get through the lecture, compressional stress is something that happens when you have plates that are moving towards each other and colliding, like at a convergent plate boundary. So let's first just examine the different types of stress that can exist. There's three different types of stress, and stress is basically the force that's acting in a particular direction. Stress is basically the same as pressure, force per unit area. So you might think about this, when you're under a lot of pressure, you are also very stressed. The three different types of stress are tensional, and tensional stress is a force that's pulling away from a surface. So you can imagine that you have a piece of chewing gum and you start to stretch it apart. And so it starts to get thinner and thinner in the middle. Those would be tensional forces. The next type of stress is called compressional. Compressional is where you have forces that are pushing inward towards the surface. So if you have that same piece of chewing gum, if you start to squish it in your hands and move your hands closer to each other, that would be a compressional stress. Now the third type of stress is called shear stress. Shear stress is basically a force that acts along the sides of the object. So it's not going into the object or out of the object, it's going along the sides. So it's basically twisting the substance along its sides. So if you had a big block like a sponge in your hands and you took the edges of the sponge and you started to slide your hands past each other, the sponge internally can twist a little bit. That's referred to as shear deformation. Now, strain and stress are two different ideas. Strain is basically when an object changes its shape when a stress acts upon it. So you can inflict a force on a particular a stress on a particular sample, and that will result in a particular change in size or shape. Now, stress will cause strain only if it's great enough to overcome the strength of the rock. So you won't necessarily always have a rock be strained. So can a rock be stressed and not strained? yes, you can subject some forces on a rock, but as long as the rock doesn't change its shape, then it's not experiencing any strain. So stress can happen without strain, but strain cannot happen with stress. So if you deform a rock, that must mean that there was some stress that was involved. So let's look at a couple of examples. Let's say I have some silly putty. If you don't know what silly putty is, you might think like I have a big ball of chewed up gum in my hand. And I squeeze it. Is it stressed? Well, if you're not sure how to answer this, you might think about pressure. Is it being subjected to pressure or force? Yes, I'm squeezing it. So the answer is yes, it's under pressure. Now, is it strained? If I squeeze a silly putty in my hand, most people could squeeze it and change its shape. So we could say in most cases, yes, it would be strained because it has to change shape. So you could squeeze it in your hand and it would change. Now let's say instead of a piece of silly putty, I have a rock in my hand and I squeeze the rock as hard as I can. Is it stressed? Well, again, I'm inflicting some pressure on it and some force, so yes, it is stress. Now, would it be strained though? Now, knowing me, I'm not a superhero. I can't change the shape of a rock by squeezing it. Most rocks are too hard. So I would say no, in most instances it wouldn't change shape, so it's not going to be strained. So let's say we look at this picture of a rock with a fold in it. When the rock formed, was it stressed? Yes, it had to be under pressure. It might not be under pressure today, but it had to be under some sort of force or pressure in order for it to be changing its appearance over time. Now, when the rock formed, was it strained? Well, the question you should be asking is, did it result in a change in shape? And if we look at this picture, we could see the layers have been folded. And folding is a change in shape. So yes, it did change shape. It might not be changing shape today, so it's not being strained right now, but in the past it did change its shape. Does the rock have any structures in it for us to investigate its deformation? Yes, the name of the structure that we would identify in this picture is called a fold. We'll look at some different varieties of folds and how they can indicate various types of stresses. I'd like to go on and talk about different types of deformation. We're going to be looking at 3 different types of deformation: elastic, brittle, and ductile. Elastic deformation is a temporary change. And so you temporarily change the shape or the volume, but then once you take away the stress, the object immediately goes back to its original shape. Now, elastic is not necessarily the same thing as your elastic band. It's basically when something acts like your elastic band, you take your elastic band and you stretch it out, but when you let go of your hand, it'll snap back into the world and back to its original shape. So in the world of science, something that's elastic means that it's a material that deforms, but when the deformation ends, it goes back to its original shape. Now, an elastic deformation is a temporary change. So if I take a paper clip and I stretch it out just a little bit, I can allow it to snap back to its original configuration. Although I can permanently bend a paper clip, and in that case, it would not be exhibiting elastic deformation. I would permanently deform a paper clip by basically stretching it out to hold too many pieces of paper. The next type of deformation that I'd like to look at are these 2 varieties called brittle and ductile. Now, both of these are permanent changes. These occur when materials deform in a more gradual sense. There's a permanent change in the shape or the volume of material. It's either caused by flowing or bending or breaking. Now, interestingly, in these 2 examples that are from your textbook, they show how you can have in a high temperature environment, like if a glass blower takes silica here under really high temperature, the silica basically just flows along and it's very liquid, and it basically deforms by bending over time, and that's essentially what ductile means, deforming by bending. Now, if I take the same glass at low temperature, when it's solidified, it forms a light bulb. And if I drop that on the ground, it'll shatter into a million pieces. And so that's what we refer to as brittle deformation. Brittle deformation means it breaks without bending. It's just it doesn't allow for any bending at all. Some other items in nature that you might have seen that would show brittle deformation would be like a piece of chalk if I were to snap it, a piece of wood if I were to snap it. And so rocks are going to respond to stresses differently. If I'm in a ductile environment, then my rock is going to flow or fold, and you'll see lots of flow structures within the sample. If my rock is undergoing at lower temperatures and pressures, it's going to undergo more fracturing and faulting, and that's an example of brittle deformation. So let's examine some of the main factors that will control whether or not we get brittle deformation or ductile deformation. These relate to the temperature, and in Earth you want to remember that as you go deeper inside of the Earth, the temperatures become greater and greater, so we're going to have different temperature regimes from the surface of the Earth versus down in Earth's interior. Something called the confining pressure, and the confining pressure has to do with how pressures will become greater. This is a typo here. Let me just fix this real quick. This is actually supposed to say pressures. P-R-E-S-S-U-R-E. As you go deeper and deeper inside of the Earth, the pressures become greater. So at the surface of the Earth, the rocks aren't under, they're not buried under as many layers, so there's not as much pressure at the surface of the Earth. But as you go down inside of the Earth, think about all the weight of the rocks on top of those deeper layers. So confining pressure is something else that will work to change a rock into a brittle deformation or a ductile deformation. The third factor that controls the type of deformation has to do with the rate of straining. So basically how fast or how slow the deformation occurs. If you have an earthquake where two tectonic plates slip past each other very suddenly, or if you have a meteorite impact, those things happen very fast and cause very sudden changes. If you have two continental plates pushing on each other, then that deformation occurs over a very slow, long period of time. The last ruling factor that will control the type of deformation is related to the rock's composition. Some materials are much more conducive to flowing and others to cracking, so depending on what they're made from. And so here's an illustration showing how, depending on the confining pressure, how much weight is all around this sample of marble. This is its appearance in its undeformed state. If it's actually completely confined with other materials around it while it's deformed, this is how it appears. If it doesn't have anything around it as it's deformed, this is how it appears. So without a lot of pressure around it, it'll actually deform in a more brittle fashion. If it has a lot of confining pressure around it, it's actually going to deform in a more ductile fashion. The rate that the rock is strained is also a controlling agent. Like for example, in this first picture, I have just a ball of silly putty that's been allowed to sit on the table for a couple of weeks. And very slowly, that silly putty is being pulled down by gravity. And so a very slow rate of deformation will lead to a ductile deformation. In the next slide, I have a medium to slow rate of deformation, and that's going to also result in a ductile deformation. So if I take the silly putty and I pinch it, it flows in my hands. But in the next illustration, if I take the silly putty and I bounce it on the table, it actually deforms quite quickly, and it results in elastic deformation. The last example here is taking the silly putty and shooting it with a gun and having a bullet go through it. And with that very, very fast deformation, it actually exhibits brittle deformation. When we get to class, we're going to discuss types of conditions that would lead to brittle versus ductile conditions. So you could look for a continued discussion of that when we get to our class setting. Now let's look at structures. The first geological structure that we're going to examine is a fault. And again, these geological structures result from different types of deformation, and we could be kind of like CSI. We could be like little crime scene investigators and go in and say, aha, I see a fault. The fault slipped this way. I could say something about what was happening on the Earth in the past. So faults are where rocks have been broken with respect to each other and offset. If you look at this picture, there are these layers that have been shifted on one side versus the other. Here I have some arrows showing the relative motion. Faults are characteristic features that will develop when the deformation is brittle. And so this is the type of deformation that we typically have in Earth's lithosphere. Now, when we want to describe the motion along a fault, we describe this using what are called a hanging wall and a footwall. And what you want to imagine is if you take the fault plane surface and you put a person on the fault plane. Let me just change the color of my pen so we could see it on this diagram. Let's make it blue. So if you take a person and put them right here on the fault plane, where the person would be standing, would they be able to be standing? That's what we refer to as the footwall block. So the footwall block is if you were standing on the fault plane, this side would be under your feet. The other side of the fault is called the hanging wall, and this is the side of the fault that would be hanging over your head. Now I have here a great movie that shows the characteristics of the types of fault motions that I'd like to have us view. Just open that up.
So putting different kinds of forces on Earth's crust, how does it respond? We can put a region in extension, trying to pull it apart. That's one kind of force that we can put on Earth's crust. We can put on what we call compressional forces here. We try to squeeze a part of the crust together. And then we have shearing motions, where we're trying to twist a part of the crust. And let's examine here for a couple of minutes how Earth's crust might respond to those kinds of forces. Let's look at extension first. So here, take foam fault, modeling an area, some pre-existing layers in here. We then put some extensional forces, try to pull the crust apart here. And one thing it can do is to break, make faults, and extend. As I pull my hands apart, the block in the middle falls down. These kinds of faults would be called normal faults, where the block above the fault moves down. And imagine this happening now, not in just one nice smooth motion as I'm doing it, but rather happening in a series of many, many jerks, and the jerks are earthquakes. So this kind of deformation is happening across Nevada and the western part of Utah in the region of the western U.S. that we refer to as the Basin and Range. So if you ever drive across Nevada from west to east, you know that what happens is you'll drive through a valley for 10 or 15 or 20 miles, and then you'll climb up a pass over a range, and then you'll drop down into another valley. So this kind of deformation, extensional deformation, has affected the Basin and Range in eastern California, across Nevada, and into Utah. And as it turns out, we have figured it out that the distance between San Francisco and Salt Lake City has approximately doubled over the course of the last 30 million years, due to extension and due to faults that operate like that. Now, take an area of the crust and try to compress it, push the ends together, and there's a couple of ways that it can respond. One way that it can respond is by making folds. We can demonstrate that by taking a deck of cards trying to push the ends together, and as I push my two hands together, then we can make a fold. So we can take these pre-existing horizontal layers, compress the crust, and make folds. So if you look at various areas in the Rocky Mountains which were exposed to compressional stresses, you'll find layers of rock which are bent like this. We have two different names for these. If we bend the layer, we make a fold so that the limbs are going away from the high point here. We call that an anticline. So it's like an A for anticline. If you fold it the other way, the central part goes down with respect to the sides. You're making like a U out of it. It's sort of a sink shape. Then that's called a syncline. That kind of a fold is called a syncline. So anticlines or synclines, those kinds of folds can accommodate compressional stress. Another thing that the crust can do when it's under compression is it can also make faults which operate in the opposite sense to the kinds of faults that accommodate extension. So take the same foam blocks here, push the ends together, and the middle block then can pop up in a series of earthquakes. So these kinds of faults are called reverse faults or thrust faults. The block above the fault moves up with respect to the other block zone. So another kind of deformation here, shearing kinds of deformation. What will rocks do in that case? On a small scale here, rocks can shear, and you can actually get alignments, interesting alignments of the minerals in the rock. These are very common in metamorphic rocks. So you can take something which maybe has a mineral in it that used to be a square or maybe used to be sort of circular in shape, and if you shear that area, then you take that circle and turn it into an ellipse. So you make these flattened, pancakey sort of structures like you tend to see in the minerals of metamorphic rocks. That's because they've been sheared. On the big scale, if you think about a whole chunk of crust being exposed to these kind of shearing forces, then you can also get faults, which will accommodate shearing. And here's a foam fault model which can represent the San Andreas Fault. So let's put it in map view here, north, up, and so to the right we have the North American plate over here, we have the Pacific plate over here, and if we put a shearing force on this, then we can make earthquakes in which the blocks of the crust move horizontally, with the Pacific plate moving towards northwest with comparison to the North American plate. So that's a model, a foam fault model of the San Andreas Fault.
Okay, so let's walk through these different types of faults again that we saw represented in the movie. A normal fault is when you have tensional stresses, so when stresses are pulling away. These are called normal because the block of the rock above the fault moves downward, and essentially the hanging wall slides in the direction that it would normally go if it was being pulled down by gravity. And that's why the fault has this name. So you could say that hanging wall block moves down relative to the foot wall. Now the tensional stresses are the types of things that we have where plate boundaries are divergent. And so if you went to a place and you wanted to figure out, what it was like in the past, if you saw lots of normal faults there, you could assume that the area was once along a divergent plate boundary. Lots of rifting deformation has been occurring in this zone. Now the second type of fault is called a reverse fault. In a reverse fault, this is the result of compressional forces. This happens when the hanging wall block gets pushed upwards. The block of the rock above the fault surface moves up relative to the block below. In a sense, it moves reverse to the opposite direction of gravity. So you could say the hanging wall moves up relative to the foot wall. And this is where you have compressional stresses. Now the compressional stresses will occur in areas where you have convergent plate boundaries. And so if you ever see this type of action where a faulted block, the upper block is moving upwards, that tells you that a convergent plate boundary existed in that zone in the past. Now the last type of fault is called strike-slip. And these will result when the motions are shear. And so in this case, the blocks are displaced horizontally with respect to each other, and they parallel the strike or the trend of the fault. Strike, the word, is used as a term to describe the direction of a fault with respect to north. We could also call this the trend of the fault. You could have a fault going perfectly north. You could have a fault going east-west. You could have a fault going in some direction around 360 degrees. So the strike of the fault is basically the orientation of the fault. It slips in the same direction as the fault, and that's where it gets the name strike-slip from. Strike-slip implies the movement along the fault is also in the direction of the fault. Now, strike-slip faulting occurs where we have transform plate boundaries, where shear stresses existed. If you noticed in the movie, they were talking about the very famous transform plate boundary that goes through Southern California, where we have the Pacific plate and the North American plate boundary going right through the land. That's where we would have a lot of shear stresses existing. In class, I will work to test your understanding of the various names of various faults. The next type of geological landform I'd like you to be familiar with, in addition to faults, I want you to be familiar with folds. A fold is a type of deformation where you have bending or warping of rock layers, indicating that the rocks have actually flowed. If you look in this picture, you could see almost like a V, upside down V shape here going down, and then another set of folded layers going up. Folding occurs whenever we have ductile deformation. So since the temperatures and pressures need to be great enough, this is only something that happens in the lower crust and within the mantle of the earth. You're not going to have folding anywhere that's shallow because the temperatures are too low. And so folding is the type of deformation that results when you have compressional stresses. And dominantly, this is going to be where we have two continental plates pushing on each other, that you would actually create these folding structures. And as we saw in the movie, there's two types of folds. There's a fold which is called an anticline, and the fold is in the form of an arch, where the rock strata are convex upward and the older rocks are in the center. So if you take a sequence of rock layers, just open up the pen here, and the layers, are initially flat, and you subject it to compressive forces along the sides, put some stresses here on the side of these layers and here on the side of these layers, I could fold these layers so they actually go in a downward arch. And that downward arch is called an anticline. You might have heard in the narration from the other fellow giving the lecture that it kind of are shaped like an A. Now this also says the older rocks are in the core. Because of the folding downward, the older rock layers, which would be lower down, are at the center of the fold. Now the second type of fold is called a syncline. A syncline is in the form of a trough, and so you have instead the rock layers concave upward. And the result of this is that if you go to the core or the center of the fold, you actually have younger rock layers because those initially formed at the surface. I think I like to remember the difference between anticline and syncline by thinking of a syncline as being like a smile, the S in smile. It's shaped in that fashion. So in class, we will go through several examples of fault types and which ones will happen along which plate boundaries, and we'll also be looking at different types of folds and their connections with plate boundaries. And so we will end the lecture here.